Hello everyone, and welcome to another episode of BMED 202. In this episode, we will look at solving reaction forces for simply supported beams. Now, when analyzing a simply supported beam, once the load or the loading is symmetrical on the beam, we can easily find out the reaction forces. Now, for this particular beam, a 6 kilonewton force is being applied at the center of the beam. This is a singular load. As a result of that, the reactions at R1 and R2 will be equal, and each reaction force will be half of the 6 kilonewton reaction force. There's a point to note in beam situations like this: the sum of upward forces, which is R1 and R2, must be equal to the sum of downward forces. So the sum of downward forces is 6, therefore the sum of upward forces, which is R1 and R2, should also be 6. And given the symmetrical nature of this loading, meaning the load is applied at the center, R1 and R2 will be half of 6 kilonewtons. That will be 3 kilonewtons, given the fact that they should add to get 6. Right? If the beam is not loaded symmetrically, like this beam for example, you'll get a situation where you will not be able to easily determine R1 and R2. As a result of that, R1 and R2, which those are the reaction loads, those would have to be calculated. Right? When we are calculating R1 and R2, we are going to use moments. So if you are not sure what moments are, please watch the previous video in the series. Now that video will be in the description of this video. Now, we can use moments to solve for R1 and R2. When using moments, we have to choose a point. Now, we can choose any point on the beam. However, in order to solve the equation, we have to choose one of the points where the loads are acting. We can choose R1, R2, or the 6 kilonewton force. However, when you choose the 6 kilonewton force, you will be presented with two unknown variables, which are R1 and R2. The aim is to choose a point such that you are only presented with one variable. That means you have to choose either R1 and R2. Once we choose any of those other points, one of those points rather, the other point will be the only variable that is unknown. I'll explain further. For this exercise, I'll choose R1. That will be my point of rotation. So from R1, we can now find the moments of all the forces. Right? The moments of 6 kilonewton, or the 6 kilonewton force, from that point of rotation is given by force times distance. In this case, 6 kilonewtons multiplied by 7 meters, and that is 42 kilonewton meters. We can also find the moments of R2. We will not arrive at the answer, but we can write out the formula. It will be R2 multiplied by 3 meters. Now, we can also write the formula for the moments for R1. It will be R1 times 0 meters. because R1 is at a distance of 0 from the pivot point. And by using that formula, we would eliminate R1, or the moments of R1, because that moment would be 0. So now we are presented with only one unknown variable, which is the moment of R2. Because we know the moment of R1 is 0. Because R1 is 0 away from the pivot point. Let me show you how those points of information will be useful. This is the beam, and we are going to work out the forces. Now, the first point, or the first rule that will be used, is this rule. The sum of downward forces must be equal to the sum of upward forces. Now, as I have explained before, the R1 force and the R2 force must be added and must be equal to 6 kilonewtons, because that's the sum of downward forces. And you'll see, once we find one of the forces, we can use this rule to find the other force. The second force, or the second rule rather, that will be critical in finding the answer will be the sum of clockwise moments must be equal to the sum of anti-clockwise moments. Let me show you what I mean. We are taking moments at point R1, where that force is. Now, we already know that R1, the moments for R1 is equal to 0, right? Let's look at the 6 kilonewton moments. That moment is 42 kilonewton meters. Now, that is a clockwise moment. R2 is an anti-clockwise moment, and that moment must also be equal to 42 kilonewton meters, right? So once we know this, we can apply this rule in a formula. There's only one clockwise moment, there's only one anti-clockwise moment. R1 will not be considered, because R1, whether it is clockwise or anti-clockwise, it is 0, because there's no rotation there. So you would neither classify it as a clockwise or anti-clockwise moment. Alright, so since the clockwise moments, the sum of the clockwise moments should be equal to the sum of anti-clockwise moments, it simply means if you are to minus the sum of clockwise moments from the anti-clockwise moments, the answer will be 0. And that is the third rule. And that is the rule that we are going to use to start off our calculations. So let's begin. So we are using the third rule, third formula. So the sum of all the moments must be 0. And we are going to use the sign conventions to determine how the formula should be written. Now, the first moment that we're taking in consideration, we're not taking in consideration R1, because you already know that that is 0. So the first one is 6 kilonewtons times 7 meters. The moment of the 6 kilonewton force. 6 sevens. So we put that in our brackets. And we know that that is positive since it is clockwise. The next moment to bear in mind is R2. R2 is negative. Therefore, we put a negative sign before R2. Right? And we can now work out the moments for R1. Not R1, the 6 kilonewtons force. That is 42. We still will not be able to work out the moments for R2. But this is what we can do now. We can bring across R2 so that the sign changes to a positive sign. And that now looks like the second rule that was illustrated, which is the sum of clockwise moments must be equal to the sum of anti-clockwise moments. Now, 42 is the only clockwise moment, so that's the sum of all the clockwise moments. R2 times 10 is the sum of all the anti-clockwise moments. Next line, you will now make R2 the subject, since you want to find R2. So by bringing over the 10 meters, it is now going to be divided, or the entire left side of the equation will be divided by the 10. Since when it was on the right, a multiplication sign was before it, when you bring it across, a division sign will now be before it. And as you realize, the meter units are cancelled out. So if you divide 42 by 10, you will arrive at 4.2 kilonewtons, and that is R2. Now if you want to find R1, you are going to apply the first rule, which is the sum of downward forces is equal to the sum of upward forces. This is simply saying that 6 kilonewtons must be equal to R1 and R2, as shown here. So this is what we are going to do. We have already established that R2 is 4.2. Therefore, we are going to make R1 the subject, which is this. So once you bring across the R2, the sign will be negative. So R2 was 4.2, positive 4.2. Now when you bring it across to the right side of the equation, it now becomes a negative number. You're going to minus the 4.2 kilonewton meters from the 6 kilonewton meters. And your answer will be 1.8 kilonewton meters. Now, if you add 1.8 to 4.2, you'll get 6. So that is proving that the sum of upward forces must be equal to the sum of the downward forces. So there you have it. And there's something that I want to explain. It doesn't matter the point of rotation. We could have also used R2 as the starting point of rotation, and all the rules will apply. Now, if you look at the first line, you will realize that I'm taking moments from R2. Now, I want you to ignore the picture. It is still pointing on R1 as the point of rotation. It should be R2. Now, if we're measuring from R2, we'll realize that you'll have a 6 kilonewton force. That is the first moment you're taking, and that is multiplied by 3, the distance. And as you will realize, the sign is negative because the rotation in this instance is negative. It's an anti-clockwise rotation. Then you will realize that R1 is positive. R1 is producing a positive movement because the rotation would be clockwise. And then that is the second rule being employed. Or the third rule rather. The sum of all the moments will be equal to 0. So if we continue to work out the answer, it will flow like this, then like this, which is the second rule. Sum of clockwise moments must be equal to the sum of anti-clockwise moments. Then you will make R1 the subject. Then your answer will be 1.8, which is the same answer that we got when the rotation point was at R1. Then you use the first rule to find R2. So it is as simple as that, people. I hope this lesson was helpful, and I hope you grasp the concept. Please like the page, or the video rather, and subscribe to our channel to receive further notification on more videos. Stay tuned and have a good day.